Okay, this is a graphing calculator question. It means you need the graphing calculator to do this. Can't do it without it. All right. Let S be this region, and the region is defined by this r of theta. As theta goes from 0 to rad pi, find the area of S. Okay, you have to remember that polar curves fill up radially. So when you have a function and you're finding the area under the curve, you're filling up this curve linearly, meaning you're filling it up with skinny rectangles, generally as you go left to right. When you're talking about polar curves, you're talking about r being the distance from the origin, and you're filling it up radially, meaning you're filling it up this way. So the way that this curve is filling up its area is actually like this, as theta goes from usually 0 to 360, or however long you need to fill up that area. Let me erase all that. It's clouding my view. And that is a fundamental concept that's going to help us out. So part A is asking for the area. The area of a polar curve is 1/2 times the integral from whatever to whatever of r squared d theta. I'm not going to develop why that is, but it's one of the formulas that you would do well to memorize. And this is a very easy problem because you just have to fill it up from 0 to rad pi. Our r is 3 rad theta sine theta squared. Okay, 1/2 r squared d theta. Okay, now your inclination is going to be you want to try to do this yourself. Don't do it. It's a calculator required problem, and your calculator doesn't even need to be in polar mode. In fact, the only time you should be in polar mode is if you need to understand what the graph of something looks like. And being that they give you the picture, you don't need it. Don't be in polar mode. Be in regular function mode. So the integral that you're going to do is the math9 command, the fnint, where it just tells you to plug in that stuff. Now, this is one variable in terms of theta, but when you use fnint, you can use any variable you want. So if you want to find the theta, find the theta. You want to change your thetas to x's, change it to x's. You want to change it to t's, change it to t's. It doesn't matter. You're only getting credit for writing this down and then evaluating it. And when you evaluate it, you get 3.534. 3.534. If you did not get 3.534, check all these parentheses. The calculator questions are obnoxious because typing things into a calculator is just really annoying. I would rather just evaluate an integral. That would make me very happy, but that's not where we are. Part B, what is the average distance from the origin to a point on the curve as you go along that curve? It's the same interval, okay? Now, distance from the origin is the definition of what r is. R is measuring the distance of where you are on the curve as you go radially in a circle as theta is increasing, right? Theta being the angle that it's making with the x-axis. So the average distance from the origin is just asking what is the average value of r. An average value is always given by 1 over b minus a times the integral from time period 1 to time period 2 of f of t dt, even if we're talking about polar. So it's very simply, right, our interval is from 0 to rad pi, and its average value, so it's 1 over rad pi minus 0, of our function that we care about, which is just this, not the area, just literally what that function is, parentheses, parentheses, parentheses. And this also is to be evaluated on math, what was that, math 9? I already forgot. I think it's math fnint, math 9. Math 9 that. Math 9 that, and you get 1.579 or 1.580. Was that the average distance from the origin? So as you go along that curve, the average length of that curve from the origin, the distance to the origin, is 1.579. Part C. There is a line through the origin with a positive slope m that divides the region into two equal areas. Okay, so basically this line has a slope of m. One of the things that you need to know is that the slope is going to be the y value over the x value, right? M equals, your slope is y over x, and y over x is always tangent. And so if we want to know what theta is, what this, right, because it's asking, what is it asking for? Right, but it's, okay, we need an integral. We need to figure out what this theta is that stops at this line. And by the way, I drew this line terribly because these areas are, pretending that this area is the same as this area, we need to figure out what value of theta that is that gives us that slope. So theta is arctan of y over x, which, and you might remember that formula from when we did parametrics and polar last year at the beginning. I don't know. I mean, this is one of the things that you need to know about polar coordinates. So does it say write but do not solve? So let's just say we're talking about this blue area right here. This blue area is the integral as theta goes from 0 to arctan of y over x. Go back and forth, whichever arctan you want to use. Arctan of y over x, which is the same as arctan of the slope. Y over x and the slope are the same thing because it wants to know in terms of m. So this blue area is going from 0 to arctan of m of the function, I'm sorry, the area of the function, and the area of the function was 1/2 r squared d theta. So 1/2 r, I'm not going to write this r out again, r squared theta d theta. Okay, so this right here is the area of the blue shaded region. And what this is saying is that the area of the blue shaded region is half of the entire thing. And the entire thing was our answer in A. So you can just say that this is the same as our answer in A. What was our answer in A? 3.534. 3.534 and half of that. So half of answer from A. Okay. Now, the answer key that's given by the College Board doesn't write that number out. They just use they use the original integral from A. I don't see a problem with writing the 3.534 for this problem. Someone might disagree with me, but it just says write an integral that talks about m in terms of the original area, and this is the integral that does that. Part D is a hell of a question. Okay, so for k is greater than 0, let a of k be the portion of the region that is also inside the circle r equals k cos theta. Now, you might not remember this, but since you have your graphing calculator, you could check it out. This right here is a circle that is entirely on the right side of the y-axis so long as k is positive, right? So r equals k cos theta, you know, is going to be like, it's these, right? So as k is approaching infinity, what's happening is k should be a circle, a ginormous circle that, pretending that's a circle, it's a terrible, terrible circle, kids, okay? Pretending that's a circle, that's what's happening as k is getting bigger and bigger. So the question is saying, what is the limit as k approaches infinity of the area of this original figure that is also inside this ginormous circle? Well, let me erase all of this stuff so that you can see what's actually happening. Okay. As k is getting bigger and bigger, what's happening is the circle on the right-hand side is getting bigger and bigger, and therefore, okay, this is a circle, pretend that's a circle, okay, is that the area of S that is encapsulated in this circle is this piece right here, meaning this piece ignoring this little sliver of that piece right there. Now, luckily, all that is the area as theta goes from 0 to pi halves of the original figure itself. So this limit, as the circle gets bigger and bigger, is equal to the area from 0 to pi of the original polar curve itself. So what we're looking for is just 1/2 r squared d theta as theta goes from 0 to pi halves, which is also something that you would just type in your calculator, which winds up being 3.324. That one was a doozy.